Okay, this is part 3 for lecture on chapter 2. We will be talking on isotopes and the atomic mass. Now, I mentioned a few slides ago that Frederick Soddy was the one who discovered that there was such a thing as isotopes. So let's talk about them and what does it mean? Well, if I'm looking at an atom of hydrogen has one proton and one electron. That is what makes up the atom of hydrogen. Hydrogen, the most abundant form of hydrogen, does not have a neutron in its nucleus. It just has a proton and then an electron to cancel out the charges. Now, a small percentage of hydrogen will have a neutron as well. So you'll find hydrogen that also has one proton, but now it has a neutron and an electron. It's still hydrogen because to be hydrogen, it has to have only one proton. That's what defines it as hydrogen. And it still has one proton, but now it has gained a neutron. So it has a little more mass than the previous version that we saw of the hydrogen, which did not have the neutron. Now it has double the mass, really, because the mass of the proton and the neutron is approximately the same. And if the first hydrogen we saw had only one proton, this has a proton and a neutron, which means it has double the mass. But it's still hydrogen because it still has only one proton. Now, so this is also hydrogen. What if now, instead of one neutron, I could have another neutron? So this next hydrogen, it's still hydrogen because it has one proton. That's what defines it as hydrogen. But now it has two neutrons, which means its mass is 3 times as large as that first isotope that we saw, the first hydrogen that we saw that only had one proton in its nucleus without any neutrons. So in all of these cases, before I go on, we have the same element, it's hydrogen, but they differ from their masses. This is what an isotope is. An isotope or isotopes are basically atoms of the same element because they have the same number of protons, but they differ in their masses because they differ in the number of neutrons that they have. The first isotope had only one proton and no neutrons. The second isotope had one proton and one neutron, and the third isotope has one proton and two neutrons. So the masses, if I'm to call the first hydrogen 1, a mass of 1, arbitrarily speaking, because it has one proton, the second hydrogen or second isotope will have a mass of 2 because it has a proton and a neutron, and their masses are pretty much equal. And the third isotope, this one, has a mass of 3 because it has one proton and 2 neutrons, which are similar basically in mass to the proton, so I can count them as 3. Therefore, they're still atoms of hydrogen because they share the same number of protons, but they differ in their masses because they have different numbers of neutrons, starting with none and ending up with 2. So isotopes, the definition of isotopes, they are atoms of the same element because they have the same number of protons, but they differ in the number of neutrons they have and therefore the mass. If we have different isotopes, then how can we figure out the mass of an atom of that particular element? Well, we talk about atomic masses, the atomic mass, and we talked about the atomic mass being found in the periodic table underneath the elements, and what you might have found interesting is that some of the atomic masses are not whole numbers. So if we're just figuring out the atomic masses by adding protons and neutrons together, that's a little problematic because we don't have parts of a proton or parts of a neutron. Well, we measure the atomic mass in this unit here. We call it the atomic mass unit, called AMU for short, atomic mass units. Now, these are very small, obviously, because we're talking about the mass of an atom. But we define, so this is a definition, and it's an exact definition, therefore, one AMU, one atomic mass unit, is defined as 1/12 of the mass of one atom of carbon-12. So if I have one atom of carbon-12 and I divide its mass in 12 pieces, one of those is equal to 1 AMU. Therefore, the mass of one atom of carbon-12 is exactly 12 AMUs, because I define the AMU as 1/12 of that mass. Now, if you look at carbon-12, as you saw in the videos, I said if you sometimes see this notation, you will see carbon-12. That tells me that this is its mass, atomic mass. So if I have carbon-12, I know that carbon has 6 protons, which means that carbon-12 with a atomic mass of 12 will have 6 neutrons as well. Therefore, the 1 AMU is approximately the mass of 1 proton or 1 neutron. Approximately. It's not exactly one or the other, because it's an average, because the mass of a proton and the mass of a neutron differ slightly. So how do we figure out the atomic mass on the periodic table? Because it isn't an exact number. It is, for carbon is 12.01, for example. Well, where did that 01 come from? Or for some other ones, I think for lithium is 6.97. Well, where did the 97 come from? Why isn't it an exact number if we're just counting protons and neutrons? Well, this comes because the atomic mass that is calculated and it appears in the periodic table, it's a weighted average of all the naturally occurring isotopes. Remember that we said that isotopes differ in the number of neutrons, and therefore, when we calculate the atomic mass, we have parts of carbon that are carbon-12. There's some carbon that is carbon-13, some carbon that is carbon-14, etc., etc. So when we try to figure out the mass of one atom of carbon, we have to take into account all of the masses from all of the isotopes, because they have slightly different masses. So we have to take an average of all the isotopes' masses. However, it's not just an addition thing, it's a weighted average, with the isotope that has the largest abundance, that is the most abundance, will have a larger weight, will contribute more, if you will, than the one who has trace amounts. This is then the formula that we use to calculate the atomic mass of every element. We take the mass of its first isotope and we multiply it by its relative abundance. How abundant is this particular isotope? This gives me the contribution, the weighted contribution of that first isotope. And then I add the mass of the second isotope multiplied by how abundant it is. This gives me its contribution to the mass, plus etc., etc. Now, all of these contributions, the relative abundances of all, have to equal 100, obviously, and therefore the mass of the isotopes, the weighted masses, will all equal the atomic mass of that particular atom. Let's take a look at how to do a problem like this. Here's a table where I have 3 different isotopes of hydrogen, 1, 2, and 3, just like we talked earlier. My hydrogen 1 has a mass of about 1 AMU because it only has 1 proton in it. And its relative abundance is 99.999%. So most of the hydrogen that is found, it is hydrogen 1, which only has 1 proton and it has a mass of 1.008 AMU. If you go to hydrogen 2, it has a mass of approximately 2.14 AMUs because now we have a proton and a neutron, and that's 0.01%. Now if we go to hydrogen 3, this is really trace, so it doesn't really give us, it doesn't have much bearing when we calculate the atomic mass. So let's apply this formula that we just saw in the previous slide to this example. I have the mass of the first isotope, which is 1.008, times, now when we do a percent abundances, we cannot use percentages, so we have to convert these numbers to regular numbers by dividing by 100. So if I take 99.99 and divide by 100, I get 0.9999. So my mass, the mass of the first isotope, is multiplied by its relative abundance, but not in percentage, just a regular number. Plus, then I take the mass of my second hydrogen, my second isotope, and I multiply it by its amount or percent abundance. So I take 0.01 and divide it by 100, gives me 0.0001. And if you do this calculation, it should give you 1.0081, or we cut off at 4 significant digits, so 1.008. And that, if you go to the periodic table, you'll see that the mass for hydrogen, the mass, atomic mass or mass number, is 1.008. This means that because most of 99.99% of all hydrogen weighs 1.008. This 0.01% is not going to affect this weight very much, and therefore the final average mass is going to be very, very close to the first isotope's mass because it is the most abundant. That's what we're going to find mostly. I have worked out 2 more examples, and I have included links to videos over here to show you how to do these. So watch these, and then if you have questions, I have this one, neon, as well. And if you have questions, you can certainly ask. This is the end then of this section, and we will continue with the mole and the chemical formula in the next section.